Okay, so we talked about covalent bonding, and we talked about how we're sharing electrons. Now we're going to look at chemical bonding in which it's not sharing of electrons, but we're going to look at gaining and losing electrons instead. So it's a totally different way of obtaining a noble gas configuration. All right, so let's review by looking at our periodic table. We know that over here, if a nonmetal is connected to a nonmetal, it's going to do it by way of sharing and will form a covalent bond. But we've got all of these metals over here in blue, and these metals don't want more electrons. They're trying to get rid of electrons. They want to lose electrons. All the metals do. Now we're going to focus on these metals, maybe get some over on this side. We're not going to really focus too much on this middle zone here with the transition metals, but regardless, if it's a metal, it's going to try to lose electrons. So we're talking about the two types of bonding. We talked about this one already. When you are going to gain and lose electrons, we're going to do what's called forming ionic bonds instead. Okay, so let's talk about what ions are, because ions are what form ionic bonds. Ions are, as it says, electrically charged atoms or group of atoms. So it could be a single atom, okay? So here is a charged, and this is the way we represent it, okay? A charged atom. Here is a charged atom. Or it could be a group of atoms. So I could have something where I have a whole bunch of atoms of nitrogen and 3 oxygen and all together have a negative charge. So if it carries a charge, it is an ion. It could carry a positive charge, it could carry a negative charge. That's what an ion is. A cation is what we see here. It carries a positive charge. And the way you get a positive charge is to lose electrons. So don't be confused with that little symbol. Don't think add, okay? That's not plus as in I'm going to add. That's plus as in a charge. And the only way we can get a charge is by messing with the electrons. So if we had sodium, and let me look at a periodic table here real quick. Sodium has 11 protons in the nucleus, and a sodium atom would have 11 electrons buzzing around it. Now we know that they're in different shells in different places, and in the valence shell there's only one electron if we look at our periodic table. But this would not have a charge. To get a positive charge, it has to happen by getting rid of one electron. So if I could get rid of that one and replace and have 10 electrons, now I have one more proton than I have electrons, and that's where that plus comes from. So it's always the loss of electrons that forms cations. Metals tend to do this, and that's what it says there, so circle the word metals. Metals, when they become ions, are going to become cations. Now let me give you a little mnemonic. Cation. Cation has a symbol inside it. Let me step out of the way so you can see it. It kind of looks like a plus sign, okay? So cations are the ones that are positively charged. Anions is the word for the negatively charged ions. So this is an anion here. They're the negatively charged one. You get negatively charged by gaining electrons. Okay, now I want to do a different anion instead of doing Cl minus, because that's just got way too many electrons for me to want to draw. Let me draw this ion. I'm going to draw O2 minus. Okay, so let's start with oxygen. Oxygen has 8 protons in the nucleus. Okay, so that's what it has in the nucleus. I know that by looking at the periodic table. An atom of oxygen is going to have 8 electrons buzzing around it. Okay, it has 8 electrons and 8 protons, and that is neutral. Now we know that it's got 6 valence electrons. We could look at that in the periodic table. What it would love to do is become like a noble gas by gaining 2 more. If it gained 2 more, it become like a noble gas, and now it has 2 more electrons than it had protons. It had a total of 10 electrons, and that's how you get a negative charge. So it's so easy to see that negative and think, hey, I'm going to lose, because every time I see that sign, I'm thinking subtract. Do not think subtract. Think this is its charge. And we can only mess with electrons. And if we're going to mess with electrons, if it has a 2 negative charge, it has to have had added 2 more electrons in there. Really easy for students to get confused by that. So this is our anion here. And I don't have any good memory device for that. Just remember cation is positive and the other one has to be negative. Now, who likes to form anions? Nonmetals do, because they're really close to becoming like the nearest noble gas. They have 6 and they need 8. They have 7, they need 8. Okay? These guys are close to being like the noble gases, and so they will gain electrons. Now I'm going to once again back up to our periodic table here if I can find it real quick. So these guys on this side, if they're not sharing, are going to be gaining electrons to become like their noble gases. Now how many would they gain? Well, these have 7, but they need 8. So these would gain 1 and become a -1 charge. These guys would gain 2 and become a -2 charge. These guys would gain 3 and become a -3 charge. Okay? The metals tend to want to lose, and we're going to talk about that more here in just a minute. Let me back up to where we were. And here we go. So when do ionic compounds form? I think there was something else I wanted on there. Nope, there wasn't. So ionic compounds are when you have an ionic bond. Okay, now we didn't specifically write that out there, but anytime you have a compound that has an ionic bond in it, it is going to be an ionic compound. Now to be covalent, it has to be covalent bonds everywhere. To be ionic, it just has to have an ionic bond somewhere in there. If there's an attraction between a metal and a nonmetal, then you're going to have an ionic compound. So they form between metals and they form between nonmetals. So let us see here if we can figure out which one of these guys is going to be ionic and which one is going to be covalent. To do that, you just have to have a periodic table handy. So I want you to pull out your periodic table and I want you to go through and decide each one of these, whether or not it's ionic or whether it's covalent. I will do one with you, okay? And then I want to have you stop and do the rest of them. All right, so let's look at a periodic table and let's find Na and let's find F. Na, there it is. Na is located right there. F, okay, so let me do a little erasing because it's getting kind of messy over here. F, our F is located right there. All right, so we have a metal and we have a nonmetal, therefore we can easily say that that is going to be ionic. Okay, you pause and try to get them all, okay, and then we will resume and I'll have answers up here for you that will make sure we check and see that you did it right. Okay, so you're back with me. Nitrogen and fluorine, we look at our periodic table. We know that nitrogen and fluorine are both on the right-hand side, so they're both nonmetals. If they're both nonmetals, then we definitely have got ourselves a, where'd you go? Oh, went too far. There it is. This is 2 nonmetals, so this is going to be covalent. Metal, nonmetal, ionic. Non-metal, nonmetal, covalent. Metal, nonmetal, ionic. Okay, so we can go through and do this. This is going to be very important that you can look at a compound and decide which it is, ionic or covalent. All right, now I kind of introduced the idea of the charge that these guys are going to get, but we need to work on this a little bit more. Back it up. Cations and anions are formed when an electron is transferred. Okay, so I said on this picture on the screen that this guy lost an electron to become a cation, and this guy gained electrons to become an anion. Where are they losing them to, and where are they gaining them from? Well, they have to pair up, okay? So if a metal is trying to get rid of an electron, there needs to be a nonmetal nearby that's wanting one, and so they'll do a swap. In this case, between the sodium and the oxygen needed to gain 2. Each sodium is only willing to give 1, so this oxygen would have to pair up with actually 2 of these sodiums. So I'd have to get a whole nother one of these with its 11 protons, its 11 electrons. He'd say, I want to get rid of one of those, and he gave 1 electron to him. He gave 1 electron to the oxygen, and that is where he got the 2 electrons from. So you have to pair it up in such a way that you can get that. So the way, whenever you get a metal together with a nonmetal, the reason they're going to be forming these ionic compounds is because the metals want to get rid, the nonmetals want to gain, they get close together, they are going to do a swap. All right. Now, we can determine how many they're going to gain or lose is because they're wanting to be like the noble gases. Now, it is easy. Let's go back to the periodic table or the image I have on the screen for a little bit and then and look at what we got here. Here are the noble gases, okay? This is what everybody wants to be like, right? These guys only had 7. I talked about how the 7A family will always gain 1, and if they gain 1, they're -1 charge. The 6A family will need to gain 2. They will be a -2 charge. The 5, well, they need to gain 3. This doesn't happen very often, but we could gain 4 in carbon. But on the other side of the noble gases, we've got, well, the noble gases are at the end. So what is this a picture of? What are we seeing here? So let's go back to the big screen and let me show you what's happening here while I take this periodic table. Okay, I know you're not going to be able to see it very well, but what we have over here, we've got our 1A metals, our 2A metals, all the way over to our noble gases. If I were to take this and loop it around, okay, and I'm going to try to line them up. I want to loop it around. We can see that I can go from 10 straight to 11. Oh, good. You're zooming in a little bit for me there. So you go from 10 to 11. We can go from 2 to 3. We're just wrapping it around there and finding the nearest noble gas. So when I look at it this way, and I'm looking at this metal here, how am I saying that the nearest noble gas is this guy here? It's like on the other side of the periodic table, but this is number 10 and this is number 11, so this is the nearest noble gas. So back to the screen here, and we can more easily see what's going on. So sodium is element number 11, but neon is element number 10. For sodium, it had 11 protons and 11 electrons. It didn't like being that way. He wants to be like this. So everybody in the 1A family had 1 valence electron. If it were to lose that electron, it'd be like the nearest noble gas. So the 1A family will always lose 1 electron. The 2A family will always lose 2 electrons and become a +2 charge. Aluminum seems really far away, but the aluminum is in the 3A family, and so it is going to lose 3 electrons and become a +3 charge. It is a very common one, so we'll throw that one in there. I will focus you on the 1A family and the 2A family plus the aluminum when you're trying to figure out what the charges are. So I would expect you to be able to look at a periodic table and know what the element is, and if it were to become an ion, what its charge would be. Now notice what I said. If it were to become an ion, what would the charge be? Let me go back to my big screen and write. Here is H2O. You need to think about what kind of compound it is first. Find your hydrogen, it's a nonmetal. Your oxygen, it's a nonmetal. We have a nonmetal to a nonmetal, so this is a covalent bond. And it's a covalent compound. Are there ions in covalent compounds? No. So there's no charges in here. So you would never write charges. You would never say oxygen has a 2- charge, because it doesn't. Here's another case where if it were to be an ion, this would be its charge. Here is O2. O2 is elemental oxygen. It doesn't have a charge. It is elemental oxygen, no charges at all. Let's say we have a piece of aluminum foil. Okay, this is the element aluminum. It doesn't have a charge. It has as many protons as it has electrons. So we don't have a charge. It's not every time we see aluminum, it's 3+. All I'm saying with this little description here, that if it were to become an ion in an ionic compound, then it would have a 3+ charge. So if I saw something like AlF3, I see metal, I see nonmetal. I have learned that metals and nonmetals are ionic compounds. If it's an ionic compound, it must be made up of ions, and now I can look at the periodic table and know their charge. Aluminum would be +3, and the fluorine, when I look at the periodic table, I see what family it's in, and we see that it's a -1, and there happens to be 3 of them, and that's how it becomes a neutral compound. It has as many positive charges as it has negative charges. So I expect you to be able to look at a periodic table and know the formula, know the charges by looking at the periodic table if it's an ion. All right, so once those ions get formed, then ionic compounds are going to exist, because the cation and the anion are opposite charges, and opposites do what? Opposites attract. Okay, so you're going to have the cation and the anion being held together by these attractive forces. Opposites attract. Once the opposites attract, that's what an ionic bond is, the attraction of a cation to an anion. So what formed the cation and the anion? They didn't like the way they were. They wanted to gain and lose electrons to become like the nearest noble gas. So they gain, they lose, they form ions, and then as soon as the ions are formed, they start hanging out together. Okay, so anytime you have an ionic compound, it's through ionic bonds. So now we've got a subdivision some more here, okay? And I'm going to draw it small in my little space that I have remaining. We had our category of compounds. That's the word I'm looking for. I can turn that into an M. Compounds. And we learned that there's covalent compounds, and now we have learned another category of ionic compounds, CPDS. Okay, so we have our further classification. I told you that these guys tend to have low melting points. These guys tend to have very high, in the thousands of degrees melting points. 1,500 degrees Celsius. That's where they would melt. Okay, always. Ionic compounds have an extended three-dimensional array. And we've seen this picture of sodium chloride before. We would always have this cation connected to an anion, connected to a cation, connected to an anion, going off in 3 dimensions until this thing is big enough for us to see the whole crystal of these guys. So because of the fact that they're large, big, lots of bonds that have to be broken and pulled apart in order to melt. In order to melt this, we're actually having to break these bonds between there. And that takes a lot of heat to do these. So I want you to keep in mind that if I can categorize something as an ionic compound, that they are always going to have, and that's an always, very high melting points. Covalent compounds don't always have low. They generally have low. Ionic compounds will always have high, so we can know something about it based upon that classification. Okay, now, how do we know how many cations to how many anions are in the formula? Sodium chloride is NaCl. That's our formula for NaCl because it's the lowest whole number ratio of the cation to the anion. How do I know that that's what it's got to be? Because a compound has to be neutral. It has to have as many positive charges as it has negative charges. That is how you are to determine the formula for it. Okay? They have to be neutral compounds. Neutral compounds have to have as many positive charges as they have negative charges. And they swap electrons to form that. So we're going to go through and we're going to figure out the formulas for these guys. So I've already done this one on the board, but we'll review it again. We have aluminum with a 3+ charge, but fluorine with a -1 charge. So it's going to be AlF3. That will give me 3 positives and 3 negatives. Now a little technique that is kind of a quick way to do it, but it generally gives you the right answer, and I'll tell you what to look for to correct it if it doesn't give you the right answer, is the power of the one becomes the subscript of the other. Okay, so we do a crisscross. So it becomes Al, the 3 is becoming the F. Okay, there is a 1 here, but do we really write those 1s in? No, we never write the 1 in. So we would have AlF3 for its formula. Now if we have calcium 2+ and nitrogen 3-, okay, we have our calcium with a 2+ charge and our nitrogen with a 3- charge. If we do the crisscross method, we see that the calcium ends up with a 3 and the nitrogen ends up at the 2. Why did that work? Well, when I have 3 with a +2 charge, I have a +6 for the calciums. When I have a 3, I have 2 of the 3- charge, I have a -6 for all the nitrogens. And now I have as many positive charges as I have negative charges. And that works. Now sometimes you won't be given the charges. We'll expect you to look them up and figure them out. So here's an example of predicting the formula that contains some sodium and some oxygen. Okay? I want you to figure out its formula, but I've got a hint for you. You're going to have to look at the periodic table to figure out what its charge is. Now once you figure it out, answer the question, and then we will resume. Okay, did you figure it out to be Na2O? Then you're correct. Now if you didn't figure it out, if you did, you can kind of skip ahead. If you didn't, then you're going to need to watch what I'm doing here. If I look at my periodic table, we see where Na is, and we see that Na has a +1 charge. When we find O on our periodic table, we know it has a -2 charge. We need to make sure we have as many positive charges as we have negative charges. So we can, I have no idea which one of these is going to take me back to that. Don't think it's this one. Oh yes it was, looky there. Okay, so we had the Na with a +, we had the oxygen with the 2-, we can think crisscross, right? And we have Na2O. Now, I need a word of warning here because it doesn't always give you the right answer. Let me show you an example where it's not going to give you the right answer. Let's say I have Ba. That's not going to do it. There's probably not a case in this class where you're not going to see it work, because I'm not going to have you have funky charges. So we won't worry about the time that it doesn't work. Sometimes when you do this crisscross and bring down, you don't have the lowest whole number ratio, but I can't think of a case in this class where that would happen. Okay, some ions are what we call polyatomic ions. Remember what poly means? It means many. Many in this case is 2 or more, okay? Not very big many. 2 or more atoms connected together which carry a charge. So I've got some common examples here, and I want to familiarize you with the names because when we get into doing our real life activity, you're going to see these names in the labels that you look at. This is called carbonate, okay? It is 3 oxygens attached to a carbon, and the whole thing has a 2- charge. Don't think that this 2- is just on the oxygen. It's not. It's on the whole thing. This one is called sulfate. Okay, sulfate. This one is chlorate. And this is ammonium. Okay, so I'm not going to expect you to memorize these, but I do want you to have them in reference so that when you're working on your real life activity, you'll be able to know when you're seeing the name of the compound what the formula is. So if you look at this guy, we see a nonmetal connected to a nonmetal. So we've got carbon attached to the oxygens with actually sharing electrons, okay? And actually it looks like this, and then if we do the whole Lewis structure, you don't need to know this, but I'm going to just show it to you. It looks like this. So we see some sharing, we see some covalent bonds, but the whole thing has a 2- charge. If I were to have this in the presence of, let's say, calcium, which has a 2+ charge, then I end up forming an ionic bond between the calcium and the carbonate. CaCO3 is calcium carbonate. That's a compound in limestone, the rock, you know. But this is going to be an ionic compound, even though it has covalent bonds in it. We see covalent bonds all over the place. Even though we have covalent bonds in it, because there is at least one ionic bond, it becomes an ionic compound. Okay, so those polyatomic ions lead to ionic compounds. Here's some other examples of ionic compounds. Oops, where'd it go? Other examples of ionic compounds, we've got the sodium nitrate, barium sulfate, ammonium chloride. Notice how I'm using those names in there. Okay. So, bonds are typically described as either being ionic, which we've just covered, or they're covalent. Okay. Those are the kinds of bonds. Compounds can be described as being ionic or covalent. So we can either talk about bonds being ionic or covalent, or compounds being ionic or covalent. I think that ends this lesson. Yes, it does. Okay, so we're finished with this description of bonding. We've gone through covalent, we've talked about Lewis structures, and we've talked about ionic bonding.